Uh, so I wanted to mention, all right, on with the show. Brad, you're up. Introduce yourself.
Okay, can everyone? Is that visible?
We say bootstrapping,
All right.
larger than the screen for the foundation.
Okay, so I'm going to talk about a colorForth derived forth that I've been working on bringing up. Let me get my cursor in the right screen. So why colorForth? It's this fun dialect invented by Chuck Moore circa 1999. There are many subvariants, but they all use color tags to dispatch on. And it's really the reason is because it has an emphasis on making Forth even simpler, and that appeals to me. So throughout this talk, I'm using some color conventions that I also tried to use in my tools. I've got these prefixes that the slide deck can actually hide them, but basically I try to use something resembling conventional Forth prefixes to indicate color transitions in case you have challenges seeing color. There are some choices that obviously don't have a single character, and as you'll see later, I use this in my tools, so I found it easier to use a single character for the transition. So this is the key. The gray words are, well, anyways. So colorForth, as folks are probably aware, uses color to encode things like defining a word, compiling a word, interpreting a word, and it has a number of virtues, but a key one is that it ends up actually, despite seeming like it's more complexity, it actually simplifies things a lot when you're implementing the core of a colorForth. So let me tell you about my high level plan for what I'm working on, and I'll sort of what motivates it. I want to keep things simple. I want to make sure that I have something that I understand from top to bottom and can kind of keep in my head. And I want to make sure that I'm building something that I can use for a little bit more than a toy. So I'm kind of keeping in mind, at least tentatively, the goal of being able to write maybe a small primitive web browser, a little bit like if you've seen Emacs, there's this built-in browser called U that is able to sort of very crudely visualize a page. So that's sort of the target I have in my head, but I don't know if I'll get all the way there, but that's at least sort of, I'm using that as a touchstone to guide me. And as I maybe a little too eagerly do oftentimes, I try to structure my Forth so that I get into Forth code as quickly as possible during the bootstrapping process. There's pros and cons to this, but it seems to be the thing I get sucked into. Names are hard, and actually noticing the naming in the prior presentation, apparently this is a common problem. I've been calling mine CF just because I needed a name within some of the source files. I clearly need a better name, but it is what it is. So for the language itself, things I wanted to do, I wanted to make it runnable directly on Windows as a Windows executable, but I wanted to try to kind of keep a partition between the complexity that Windows brings in. So I've tried as much as possible to have sort of a loader and sort of I/O dispatcher from Windows, and then have that be its own thing that sort of contains the complexity of Windows outside of the Forth, and then transition into a native Forth inside. I've tried to leave my options open, which maybe is a bad choice, but basically I've tried to structure things in a way that give me the option in only Forth code to go change what register conventions I'm using. And then the other thing is that I vacillated a bit and ended up deciding to do what is a 64-bit Forth internally, but it's 64-bit in the sense that it has 64-bit data. but uses 32-bit addresses. So this is sometimes called an x32 addressing mode. So it's running with the x64 instruction set and is able to do 64-bit addresses, but if I've mapped things such that everything falls in reach of the bottom parts of memory. Moreover, I've gone with word addressing, except that there are places where that hasn't worked out so well, which we'll talk about. I've tried actually to retain a lot of the quirks that are in sort of the most conventional version of Chuck's Forth, just because I wanted to give it a go. I don't think I'd ever sort of earnestly done so, and so yeah, that's what I've done. So I've kept sort of some of the quirks like minus as invert and or as XOR, and some of the unusual choices with flow control. And as well as word size indexing and using an A register. And I haven't implemented this yet, but the transition from immediate to green being compiling a literal. So when Chuck, that should have an apostrophe, but when Chuck has bootstrap forths, I have the sense that his steps are he writes the editor and the core and ASM and then sort of builds up the rest of the system. I haven't quite done that, and I don't know if it speaks to my proclivities, but what I've done is I devised a text syntax to allow me to be able to sort of check in and out my work in a format that I could preserve easily in conventional source control. And then I've written a converter that converts in and out of the syntax. And then I quickly found that, well, I wanted to see the colors, so I wrote a syntax plugin for my text editor Vim. And then from there, I bootstrap from a minimal colorForth, and then write the rest in colorForth. So I'll walk through how that works. So I've gone ahead and used used Chuck's encoding from sort of the most widely sort of disseminated version of his colorForth, partially just because although there are possible alternatives, it seemed like a thing to stop me sort of infinitely regressing on whether to do some other encoding. It has one virtue that I really like, which is that it encodes numbers in a pre-parsed form, so it immediately kicks out a lot of the complexity of parsing numbers from the parser, and it has a similar property with strings. So the format uses 28 bits to encode the in variable length character encodings, characters of the word. There's 4 bits for the tag, and then for encoded numbers, there's 27 bits to use for the content of the number, and then your there is a format that supports using an entire word to store the number. I've ended up for now actually disregarding that. It turns out most of the time you can get away with smaller constants, especially if you're sign extending them. So so I've stuck with Chuck's encoding in terms of the tags. I have for the time being retained the comment capitalization, but what I've ended up doing so that I have a way to easily convert back and forth with fidelity and store it in version control, I've used a set of prefixes in text. So they're the ones you can see here. So like a tilde for magenta or variable words, a right bracket. And then when there are numbers, that's a further prefix. So I put a number sign in front of decimal numbers and a $ in front of hex numbers. And so the combination of the two allows a relatively simple converter to convert back and forth between them. I've used Chuck's table of variable length encoded characters and kept his character set. I've noticed actually one thing that crept into, I think, Howard's variant is that there was at some point a replacement of the apostrophe character for a semicolon. So that seems to be a bit of variability actually in the encodings out there. I don't particularly need the colon, so I've kept the tick for now, but we'll see. I haven't written the editor yet, as you'll see. So the conventions in the text is these prefixes, as we just talked about, number signs, $signs. I also use a backtick so that I'm preserving cases where you were not able to fit the word into a single 28-bit cell, and that allows me to be able to sort of losslessly convert back and forth between the binary representation and a text representation to check in. I wrote a converter in Python. I actually vacillated quite a bit in the converter. You can end up getting sucked into this because I started with like, oh well, let me make sure I can encode and decode some of the files that Chuck has, and oh, then some of Howard's, and he's got some quirks in his as well. I ended up sort of starting down the road of something a little bit like Dennis's converter with the sort of making it much more like a conventional fourth, and then found that I wanted to preserve the property of sort of fidelity of any bytes going in, and sort of the exact byte representation going in and out. So after some thrashing around, I finally said enough and paused where I was at with a converter that can go back and forth. And again, the main goal is just to be able to check in and out source into a version control system that doesn't understand binary very well. So it basically can either read in a file with some blocks and spit them out. Oh, I forgot to mention, there is a prefix for the screen number so that the file can also contain multiple blocks and then sort of skip over gaps. So then I wanted to be able to see the colors. I happen to use Vim normally. If you ever want to have a viral editor, the trick is make sure that it has unusual keystrokes in terms of how you move around and enter and exit editing modes, and then everybody who uses it will be addicted to it and can't leave. So I decided to add syntax highlighting. I've done this actually once before, just for Forth in general, to sort of color it in a colorForthy way, and then somehow managed to lose the syntax files. It's not too hard to do for this primitive encoding that I've got. You have sort of one file that says, well, for this extension, associate it with this particular type, and then you can just have a series of regular expressions that lets you specify how to highlight a given thing. And so, with a small file, I'm able to then open up a file that contains encodings like the one you're seeing in this slide deck, and see the colors. Interestingly, I also, for this late last night, I realized I wanted to have colors in the presentation, so I decided to edit my my slide presenter on the web and have it also do a similar kind of prefix detection to inject colors into the slides. So my process in bootstrapping is basically I started with a C interpreter that knows how to execute a very limited set of words that are just enough to kind of get the world turning, and then I make just enough machine code so that I am able to have the C code thunk into Forth code via a word that is defined. And I should point out that the constraint I've assumed is that the C code does not know anything about the register conventions that will be used in the native Forth, but it does know the layout format of the dictionary. So that's the sort of trade-off. The C code needs to sort of internalize the dictionary conventions, but it doesn't need to know anything about the register convention. So there's a thunk that does the right register transitions to convert from the C calling convention when you call into a Forth word, transitioning sort of where all the registers are at, and then it's able to execute a word. And then after I can execute a word, I then build up the ability to compile a word, and then shortly after build up the ability to compile a number. And each of these are sort of hooks that the C interpreter knows how to transition into. And then once I've got these, I pretty much can't have all of colorForth, with the exception that it's not dispatching through its own dispatch table. I build up sort of the core words and macros, and then implement the color words in dispatch, and then I transition into running completely in machine code, and sort of in the C interpreter drops away at that point. So so initially the set of words that I have to bootstrap the world are pretty limited. Compile a single byte or 2 bytes or 3 bytes. Oh, I forgot one, or 4 bytes. There's a comma that's missing. To load a block, to switch between forth and macro words, and then the ability to execute numbers. So that I should point out that also means that the C interpreter assumes that it knows enough about the stack layout, and the thing that it does in the thunk is it actually passes the data stack in as a parameter. So, and then for debugging, I quickly found that I needed a word that can show me where the dictionary here pointer is, and some ability to print, or else things are miserable. So, these words are just implemented. It's a very small interpreter done in a handful of lines of C code, where it's able to add words to the dictionary, or into the heap space, load words, and there's this is a subsection of the load word, which has the whole interpreter is just implemented inside of load. And we'll see the outer structure in a second. And then transitioning between words. So not a lot of C bootstrapping. And then at that point, it's loading from these blocks that I've encoded. And so I've got a sort of a start block that at 0 that describes my register conventions. I actually thrashed around a bit with register conventions. Initially, I started with, so I think I always had RAX as the top of the stack, but I went down the rabbit hole of I was using RBX as a stack pointer, and originally I was actually going to use a wraparound stack that's limited to 64 cells by just incrementing and decrementing the lower part of BX. And then I found that this actually made bootstrapping harder, because the kinds of instructions you have to encode to make that work nicely are larger. And one of the appealing things about some of the register choices that Chuck made is that it actually leads to some terser instructions to encode. And so I pivoted back to using something a little closer to what Chuck uses in his forth. So an RSI for the stack pointer. I ended up putting the heap in RDI, because then I can use some of the string instructions to write things into the dictionary. And then I use some of the upper, R8 through 15 for other things. But basically, I used R8 as the a place to sort of park a reference to the base of the environment that C knows about. And most of the registers are unused, and like RCX and RDX are temporaries. I kind of tried to walk around the set of registers in the C calling convention, because there are some registers that in the standard C calling convention are guaranteed to be unused when you transition in, or used for parameters, and there are some that you have to save. And so I was trying to sort of minimize the thunk in. So the memory layout of the system, I'm able to use some virtual allocations to allocate a bunch of memory just up front. So I just go ahead and reserve a gigabyte of virtual memory. It doesn't actually, capture that much, but I just, grab a big chunk of virtual memory. And then I stick a small space of 256 bytes for a data stack up at the top of that range. I have a place to park the data stack pointer and the heap pointer when you've transitioned out to C, because you don't want to have them in a register when you transitioned out to C. And then I've got some pointers for the active dictionary, and then the end of the forth and the macro dictionary. And then there's an entry point where the system calls into once you've sort of everything's been bootstrapped, and then some other things that I'm stashing, starting from about number 6 on that list. Everything is happening inside the bootstrapping code. And then lower down in memory, I've got space for the forth dictionary, space for the macro dictionary, the heap for compiled code, and then the loaded blocks. And the C harness for the whole thing loads the blocks at the beginning, so they're all sort of sitting there to use, so you don't have to know anything about disk IO or things like that. There's a bunch of macros in C that I'm able to use to make the interpreter fairly dense, that sort of encode this convention in some macros. And then calling just becomes a matter of using that thunk that I mentioned, the C to F word, which is the very first word that you need to define, and then you're able to use a C function call where you know the register convention because of the calling convention of the machine, and then transition in. So at this point, I've got on block 1 this big thunk that's a little bit tedious to hand assemble, but it's basically setting up the flags, transitioning storing some of the registers to the return stack, and then setting up that calling convention, and then eventually calling into the address of a fourth word with a fourth calling convention. And so once that's done, you can now execute words. And then similarly for literals and compilation, a little bit of macro glue can allow you to have C use the thunks in forth to set things up. And then as I mentioned, the dictionary convention is encoded. So unlike Chuck's dictionaries where there's sort of two pointers two arrays with the words and the addresses, I decided to interleave them because it was less juggling of variables. So I interleave word, address, and then use a null at the end to mark the end of the dictionary. And then there's a pointer to which of the active vocabularies, whether the fourth vocabulary or the macro vocabulary. And then find, I'm able to just have C, so the C interpreter understands how to walk this dictionary, look for a particular word, and then can jump there. And so then I'm able to, so I need to then bootstrap compilation of words and compilation of literals. To do this, I found that having a word that, so I called it 1, that compiles a word that compiles something which compiles a particular byte, ended up being a useful construct. So it is compiling a word that will then compile a word. And using this, I can then build up semicolon, I can build up comma, and then I can from that build up comma compile, which knows how to compile a call into a word. And then I apparently skipped over, oh, weird. I skipped it. Apparently I'm missing a slide here. I am missing the definition for literal, but, and then zooming out a little bit, this is what the C interpreter looks like. So it just knows how to decode some of the colors. It knows how to dispatch through these thunks into forth, and then it just walks over a block dispatching. So, yeah. And then I go and I build up sort of everything else. So I create a bunch of macros for building up each of the words in assembly. Many of them I do actually as macros so that I get them sort of compiling inline assembly. They are macros that sorry, here is literal. I'm mistaken. It's on this next page. So I'm able to build up dupe and then literal, and at that point now I can compile literals and compile words, and sort of the real business of the thing can begin, and you're sort of in a conventional colorForth at that point. So you can define, I then go ahead and define drop, and I redefine all of the comma words to be able to have them exist in the dictionary that will exist after the C interpreter goes away. And you'll notice that they end up being mostly single line, because typically I'm able to sort of build up in a way where I'll define nip dupe, which needs one additional instruction, and then on top of that I can define dupe, introducing one additional assembly language instruction. So the difference between most words as I define them ends up being basically adding in one additional assembly language instruction. What I was trying to say before is these words are all in the macro vocabulary, so they are words that compile assembly or machine code into the current word when they're compiled. And then from there I build more nip over. I have this word aside that I ended up using that stashes our RAX, the top of the stack, into the temporary RCX, because there end up being a bunch of cases where that's useful. I use it for swap, and I use it a few other places. A lot of the store operations, this ends up being handy. I ran into some pain with using the X32 numbering convention that I mentioned before. It ends up being annoying that when you're dealing with x86 instructions, you very much want them, you want to be using byte addressing because they are variable length in bytes. And yet I was trying very hard to use an addressing convention in which I'm operating on words. And so I ended up having to have parallel definitions for some of these. And so I'm torn. It ended up being, I think, more complexity to do word addressing, even though it is awfully nice to be able to just do a +1 and a -1 to increment addresses. So I've struggled a bit with that. I have words that do Chuck's address a register using RDX for that purpose, which I didn't put in my diagram earlier. And then I go and define arithmetic and star slash and some shift operations. Ended up being useful for reasons. And then I'm able to go ahead and define the one flow control operator, or the two that Chuck has, which is just if and -if. And I should mention, actually, by the way, I elided one detail back here with semicolon. Oh, sorry, we haven't gotten there yet. Never mind. So
Brad, are you taking questions?
yeah, please interrupt me.
What is -if?
So -if in Chuck's convention is it is equivalent to, let me rewind, I actually had that in a slide here. It is equivalent to checking to see if something is below 0. So here it is. So it's equivalent to like a dupe 0 less than if. And the key thing about Chuck's flow control choices is that his if does not consume the value on the stack. So it's in a conventional forth, it would be sort of like a dupe if, and so you have to you have to take into account that there's that extra value there, and it ends up being useful oftentimes. Typically, if you're doing a comparison, you oftentimes want to have the value stick around. So yeah, that's what a -if is. Confusingly, the minus, as he uses it, is an invert, which is super confusing, although it does kind of weirdly grow on you, actually, I've found. So let's see. So anyways, from there, I then transition into words in the fourth dictionary. I make this is just a screen full of words where I am basically using the macro to compile the assembly into a word that's sitting in the fourth dictionary. So where the other words are words that live in the macro dictionary and will compile these low level opcodes into the current definition, so you get them kind of inline. This is creating them so that they exist in the fourth dictionary as actual words that you can execute. And then I'm even able to define, I dodge needing to have a separate color for finding the address of a word, but because I'm able to define a tick word in a fairly convoluted way, where you jump into the tick word, it looks at looks at the return, the value on the return stack, and skips ahead and is able to jump over the word that you would have returned back to and convert that call into an address. So you're able to get the address of a word without having to have a separate color for it. It's a little bit awkward, but it does work. And then I have some plumbing to expose all of those system variables that I mentioned that sit up at the top of memory. And then and this is sort of, I guess, let's see, and then a little bit of sort of bookkeeping for so invoke is a func that lets me transition back into C. So imagine now I've called from C into Forth, and now I got to be able to call from Forth back into C. So that's what invoke does, and that allows me to at that point transition having the print word be a word that I can call at compile time instead of just execute time, which is immensely helpful for debugging. And then I think these are probably the most interesting two slides in the innards, because this combined with this is sort of colorForth in its totality. So these are dispatch words that implement what it means to define, what it means to compile, what it means to compile a number, what it means to execute or execute a number, what it means to define a variable, and so on. And so these are the sort of color definitions. And then I'm able to just build up a table that is a dispatch to those. And then interpretation then just becomes walking that table, walking a series of addresses in memory, looking up the color in that table, and then calling that particular word. And so sort of imagine writing colorForth in colorForth. This is colorForth in colorForth, which is, I think, sort of gives you a sense of what is appealing. And this is probably more complicated than it needs to be, because it exposes some of the stuffing of my particular implementation choices. And so I think, trying to convey to folks why colorForth is appealing is that this is a lot simpler total sort of core to the interpreter. So if you're so that's that. And then at this point, I can then now load things, and now at this point I'm in the sort of a standalone colorForth and have bootstrapped things. And in the harness on the outside, as we'll see in a second, I have the ability to display. I have a region of memory that I've dedicated to draw to, and I use a Windows call to copy this onto the screen. And so here I just have a small test where I'm filling in some colors. And to give you a sense,
Brad, before you go on, can you go back to that screen? What is the right bracket?
So this is just a crutch to be able to encode it in text. So if I turn off the encoding, really what you've got is sort of this in your head, where you're seeing just the numbers and the colors. But this is the format that I use. I'm doing this for two reasons. One, sort of colorblind sort of aid, but also I want to be able to store my source code in plain text, so I can check it in and out of Git. And so I'm using this convention for now. Once I've got an editor that's up and running, I will be editing just directly in colorForth. And then if I save it, you'll see this if you checked it in and out of version control. But the eventual intent is that you would use it in this way throughout. Does that make sense? So pretty small so far, 256 lines of C code. The converter ended up being shockingly complex at 234. And then about 259 lines of colorForth, and there's some make files to glue it together. So it's a pretty small chunk of stuff. What's left? I haven't really fully integrated with the Win32 bridge. Like, it knows how to, I can draw into the frame buffer that I've got set up, but it doesn't know how to do anything interactive yet. I need to write an editor, which I got very close to finally being able to do just the other day. Then I kind of want to make it simpler, because as I sort of did this process, I was doing it incrementally to sort of learn what worked well. I'm really torn about machine word indexing. I feel like it's nice once the system is up and running to be able to think about just words, instead of bytes. But it's really hard during the bootstrapping. And I struggle. If I was targeting like an ARM architecture where all the instructions are word sized, then it would be nice and beautiful. But with x86, it feels sort of awkward and icky. And I wonder if maybe the problem is I'm too worried about retaining the ability to manipulate the x86 instructions directly with loads and stores, and maybe need to be thinking about it somehow differently. I have a bunch of words in the bootstrapping that I didn't end up using. I sort of, assembled a bunch. I sat there with an assembler and assembled a bunch of stuff by hand, sort of one off to capture them, and then I sort of assembled more things than I really ended up using. So I can probably pare things down a good bit. I kind of have wondered if I should have just started in ASM. One of the things about the choice of having bootstrapped with a C interpreter that then loads a bunch of sort of a quasi colorForth to then load colorForth is that you're spending a lot of time sort of in C, a lot of time in the bootstrapping, and maybe Chuck's got it right that you just write the thing in assembly. The problem I guess that I have with that is that then you're forced to you're then tempted to write the editor in assembly, and at the point you've written the editor in assembly, that now sort of the system isn't as refinable. So I'm probably going to stick with this for a bit. I guess if I had locked in my register conventions, I probably could have simplified bootstrapping more. Maybe I could have structured things in a way where there's still a C harness, but instead of having to write the bootstrapper in Forth, I could have maybe written a little bit of inline assembly or something to make that transition nicer, so that there's sort of less of this sort of bootstrapping the world when you don't have anything there left. I'll do a brief demo, and then if there are any questions, let me quickly share a different screen. Actually, I think what I'll do is just share the whole screen. There we go. One thing actually that this process prompted me to think about, making yet another Windows app. So here's the icon for the thing. I actually, if folks have been paying attention with MicroEForth, I went and changed the icon for it because I was noticing that literally, I think I was using like something like 200 kilobytes just for the icon because I have this beautiful icon. It occurred to me there's something kind of odd about having a Forth that where the executable, more of the size is being spent on the icon than the size of the Forth itself. And so I switched to MicroEForth to use what is actually a 16 by 16 color icon, and I did something similar here for this thing. I'll run the sort of that demo in a second, but let me just quickly pop into the source code here. So it may have been a little. I'll just show off that the bootstrapping code. This is what it looks like in Vim, where I'm able to just sort of have the text. It's not the greatest place to edit colorForth, and it's very annoying to have these tick marks that you get for longer words. I have a step where I convert in and out again, and it will be smart about dividing them up. And this is again because not every word will fit in 32 bits, unfortunately. I was tempted to do a 64-bit colorForth, but I for reasons I debated and ended up not. And then to give you a sense of the C code in total, it's not a lot to bootstrap things. A lot of this is actually just code to draw the frame buffer, and I've even got some junk commented it out. And a lot of this is just boilerplate just to be a Windows app. And then the sample I'm going to show is just this little program at the end here where I'm not even using square and cube, but what I'm doing is getting the address of the display buffer, getting the address of a particular row, setting up some colors, and then I'm using fill to fill in individual stuff. I'll just run this, and oops, it went to the other screen, but there it is. And so it's drawn into the frame buffer. And at this point, like Forth exited after it filled in the frame buffer, so you're just seeing the frame buffer at the end. But it's just drawing those 4 lines. So next stop is having an editor, and I'll take questions.
I have a comment.
Sure.
Computers and computer operating systems are so complicated today. it's obscene. And I think when you talk about implementing this in Windows, I mean, the whole point of Windows is make it, it should be easy for a programmer, just paint stuff in a window. And it, I just, I think computer science is completely broken today. I really do. We'll talk about when I do my talk. I think you'll see that if we just trash everything and start afresh on our own hardware, get the Forth community going. I mean, you're so smart, Brad, spending that time wrestling with Windows. I know you have to do it at work, but I think I don't know. I think it's all so hard. I'm an embedded programmer, so I come from a different space than you do. You work at Google and you do all this really incredible stuff, but don't you think computer science is too hard today?
It's absolutely gotten out of hand, and I guess the challenge for me, is Windows, for example, brings in the minimal hello world in Windows is huge, and I think that the way I've tried to sort of contend with that is to think, okay, there's all this complexity that comes from all of the design assumptions that have gone into a conventional system. At least if I can devise a partition between the two, and I can kind of have the complexity pay down its own cost. So like one of the reasons that way back with RainbowForth, what I tried to do was bootstrap, be able to call into Windows and Linux from colorForth in a way where I was still interacting with Windows. And with this one, I thought, well, that's not useful, because then you're dragging all that complexity into Forth. And so what I've tried to do here is try to keep a cleaner partition of, I'll use Windows to bootstrap, to load up a file, to set up my memory, to set up my, get the CPU in the right mode so I'm calling my instructions. And then I'll try to not be out in that world and be in this other environment. But the fact that you're even running, that we're talking through a very complicated piece of software running on this very complicated operating system across, all sorts of protocols to make Zoom work and so on. I don't know. It's hard to have that clean partition, and it creeps in, right? Like how a lot of the jumping, and if I had started with a bare metal thing, maybe I would have not had to do all this thunking back and forth to C, for example, because all of that is just a convention. It's not even the x86 instruction set that requires all this. It's that you're interacting with the convention that's been established by the C compiler and how it wants to allocate its registers. So yeah, I don't know. It is as you say, a lot of complexity.
Brad, a quick note, if you don't
Great
mind.
work.
Yes, Stephen.
Brad, I hate to say this, but you're fighting the operating system at this point.
Yeah.
Yeah, and there are better alternatives.
One thing I would like to add is why don't you start a fresh, target an embedded platform, start from ASM from the ground up, and create something that works purely on bare metal. No Windows, no Linux, none of that. Because that's what I did. I wrote a couple forms that were written in C and ran on top of Linux and all that. And I discovered that my token threaded Forth for Linux is no faster than Python, even though it was running on an over 2 gigahertz processor. So I said, screw that. I'm going to go and target these microcontrollers and write my code not in C, but in assembly. And and I'm going to compile to machine code from the ground up. And why don't you do something like that? Because then you have none of the complexity of a commercial operating system or even Linux.
Break. We have to move on now. That's a topic for another day.
I just have a very quick comment. This is the man that created ESP32 for it. It's a great embedded for it.
Greg, the problem with that is the device drivers. It's
break. Stop. Everybody stop now. We're going to move on. Like I said, topic for a day. We could go on for another hour with this. I hate to do this except on fourth day, but let's make believe we're trying to get to the end of the meeting at noon rather than
I'm ready.
30. But first, I have a quick. This might take 30 seconds.